And I think I figured out a way that I don't have to wear the headphones and I can capture your audio and my microphone at the same time. So hooray. Can someone say something just so I can check?
Friends don't let friends smush.
Hey, thank you. That is correct. That is a multi-level modeling joke, by the way. Yes, you will all be privy to all our terrible stats jokes. So yes, on that note, Vladimir, what I was going to say is that no, there is no good way to protect yourself from this kind of weather, and that is why the public schools have a rule that if the forecasted temperature at 10 o'clock through some combination of air temperature and wind speed reaches a wind chill below a certain point, they shut down school for the protection of the little kids who are sitting at the bus stop freezing their butt off. But as it turns out, graduate students have skin also, as do faculty, staff, and everyone else who might have to catch a bus or park their car and pray that it starts when they get back to it. So, in addition to needing to be on parenting duty today, I take it seriously when the weather is that dangerous to send people outside. So, we're here again. I swear we are going to get to a classroom at some point. At some point, that is my objective this semester. The first semester I moved here was January 2019. And during that first couple weeks of class, I had to teach from my basement for like 5 classes in a row because we kept having snow days and cold days, and it just seemed like it would never end. And I get the sense that this may be on a similar weather trajectory, but we have better technology now. Thank goodness. So welcome back, everybody. Have your caffeine of choice, your lunch of choice. I've been up way too long. I need the real stuff today. The placebo is just not going to cut it. So anything you wanted to chat about or ask about before I dive into announcements and other stuff? Not yet? Okay. Then let me get things rolling here. I'm going to enable the transcript so that you can see Zoom's attempt to translate my words. And now I'm going to hide it from myself so I don't lose my mind. And now I'm going to share the screen so that you can see what I see. All right, there we go. And now I'll hide the controls so I don't lose my mind on those. Where are they? I just saw it. Hide floating meeting controls. There we go. Participants can now see my screen. Excellent. By the way, one thing that I figured out later than I probably should have is that when you're looking at a shared screen, the view menu that is in the top right corner, there's a view where all of your heads are at the top of the screen and it can only fit 4 or 5 people. There's another option in that same menu where your heads show up on the side instead. And if you select that option, you can drag the window so that the shared screen is smaller and you can see more of your classmates or fewer of your classmates as you prefer. So if you're somebody who wishes you were in person and you miss human contact and you want to see all the smiling faces that I can see simultaneously on my 2 monitors, then choose that view so that you can see more of each other. But the view that I wanted to show you is the course website because I made some updates to it today that I wanted to make sure that I pointed out. First off, the homework system is live. So you get a chance to practice doing homework by completing homework 0 over the syllabus. And I have recorded a video that goes over the homework and navigates and provides commentary about its features. That is linked right here. So I would ask that you try your hand at homework 0 before next Monday night. There's no points if you're late, but if you do it at some point, preferably soon, you'll get 2 points of extra credit. So I do this just to make sure that everybody can use the system, to make sure that I have everybody's names encoded correctly and that kind of thing. So if you are unable to log in, please let me know as soon as possible. If you click the link to the online homework system, it will bring up a tab that looks like this. And the last name that you put in is whatever Maui thinks your last name is. That means if you use two last names, it's both with a space in between or a hyphen in between or whatever combination that you have. If you want to change how you log in, if you're changing your name or something like that, let me know and I can change the database. That's not a problem. And I do need you to know your 8-digit Iowa ID. So that's what's on your little ID card. It should be somewhere in your login information for the university. And most web browsers will save it for you after you enter it once. So you only need to remember it one time. So that's how you access the system. It should take you a good minute or two to do this homework, right? This is not a real homework. This is just questions about the syllabus designed to illustrate the system. And if you've been through my classes before, you have done this before. It is the exact same setup, although the questions have changed slightly for this semester. So I will let you have a chance to practice that, preferably by next Monday night. That way I can troubleshoot any problems far in advance of when your first homework will be due, which will not be until week 4. Other things that I have put up include your first formative assessment, but that's not due for another week or two. Most of the questions are things that we'll go over next week, so you don't need to try to work ahead on that. And last but not least, I am currently in the process of building the materials for next week, and in doing so, I decided to add another article. So this article right there has been added to your reading list. It is uploaded into files separately on Icon. So in Icon, there's a big zip folder of all the readings that we started with. If I add any to the list, I'll just post them individually. That way you don't have to re-download the entire packet of readings. And I also updated our syllabus, the printable version, to include the reference for that additional article and to acknowledge that we are meeting on Zoom. So the printable version of the syllabus, I do not update unless there's something that's a major change. I do it periodically through the semester, but by the end of the semester, you will have a printable version that reflects what actually happened as opposed to what I had planned. So that way you can take that with you and have a record of what was actually covered in class. So I think that was all the announcements that I had. Any questions on that? No? We're good? Hello? Yes, not rhetorical, I swear. We're good? All right.
Yes, yeah.
Good, excellent. I did post 2 new things. These are just extra resources. I'm going to show you an Excel sheet that I made to demonstrate a point, and I thought, wouldn't it be nice if they could play with it with me? So here it is. I put up an Excel sheet. You can download it at your leisure. And there's also a little SAS program that goes with it that I'll explain. So those are just extra things for you to have. You don't need to print them or worry about them otherwise. So shall we jump back in then? Why not? We have the rest of lecture 0 to finish. We were starting round about here. I wanted to start back with this slide. This is slide 14 in lecture 0 because I realized I may have forgotten to make a point about the readings. So each unit that we have that is a combination of a lecture and example, when the unit is sort of started on the syllabus, there's a whole bunch of readings listed for that day. I did not intend for you to have to read everything for that one class. It's just that those are the references that go with all of the concepts to be presented in that unit. In terms of a strategy for doing readings, I would actually wait. I would wait until I get a chance to introduce some of the big picture ideas, and then I would start reading. Because I feel like the details will come easier if you have a framework in your head as to what this is even about. So there's no pressure to have to do the readings by any certain day. A lot of them are sort of for your future reference and further examples in addition to just what we're covering. So I know there's a lot of readings. I don't have an expectation that you have them all read by any certain day or even at all. I just want to provide additional resources, things that I have seen and found useful. So in terms of prerequisite stuff, next week we're going to practice a little bit with interaction terms in particular, because that is a topic that I have found great heterogeneity in how it is presented from other instructors and in other classes. And it's something that if you don't have a decent handle on it, then this class will be harder than it needs to be. So my logic is let's make sure that we get some practice with that within the context of the models you should already know, general linear models, ANOVA regression, that kind of thing. And then when we start messing with the y side of the equation for the rest of it, it will look not quite as unfamiliar. And I do have material posted from another class that you can visit if you'd like a greater treatment than what we'll do just next week. So, any questions on prerequisite familiarity stuff? No? Okay, cool. Moving right along then. We talked about this last time, what we're going to attempt to cover in this class. We were able to get through all of this the first time I taught the class, even though we lost a week. So I'm optimistic that the week we're going to spend reviewing next week will not compromise our ability to get through this material, but you never know. All right, so the bigger picture. I want to give you just a broader sense of how what we're going to talk about fits into other things that you either have learned or will learn. Ideally, if I had a sequence in mind of how the classes that we offer in our program would fall, I think that this class that you're in right now comes straight after intermediate statistics, so the general linear models course. So for those of you who just got out of that, you're right where you need to be. Some of you I know have already taken advanced coursework, and so this is in some sense below that in terms of complexity, but it's still sufficiently different that I think that even if you've had other courses, there's still things that will be new to you. But I feel like it helps to see how it all fits together and to describe how what we're going to do is the same as what you know and then how it's going to be different. So I wanted to give you just a bigger picture background today about where this came from and why. So Legos. Those of you who have children will recognize these things as what you do not ever want to step on if you have bare feet. They hurt. But Legos are a source of endless fascination. They were around when I was a child. My child has Legos. Legos will live on for the rest of eternity. And the cool thing about Legos is that even though each of these tiny, tiny little pieces by itself is very simple, when you put them together, you can build amazing things. So this is Legoland at the Mall of America, and there's Legolands throughout the country. And why I'm showing you pictures of Legos is that I feel like this is a very good metaphor to describe how I think about quantitative methods. When you think about a method, there are building blocks that go into it. And when you think about how do I know which model I need? Well, okay, what kind of building blocks do you need to go into the model? You need to pick up different features from different things that you've learned. And if you understand these features as modular components that you can add or remove as needed, then you have way more flexibility in designing exactly the right kind of analytic approach for the data that you have. So our worldview is that there's 4 Legos that make the basis of all of quantitative methods. And linear models is what you've already learned. That's just the first one. So where this viewpoint originally came about was in trying to articulate why it was that when I first started teaching upper level courses, so when I first started teaching courses on longitudinal data analysis, structural equation modeling, things like that, I was at the University of Nebraska-Lincoln in a psych department, and I was teaching students who had classes on regression and ANOVA and design, and they were coming to me after that. And folks had a hard time, and I was trying to figure out how I could make it better. And I realized that there are a lot of concepts that are brand new in those classes that are taught at the same time that don't need to be. I see, Kaylin, you're shaking your head. Yes, there are a lot of concepts that are new at the same time, but they don't have to all be taught in that one class. The building blocks, actually, of what makes the complexity don't have to do with structural equation modeling per se, or longitudinal analysis per se. It's the combination of everything at the same time that gets overwhelming. So I've spent many years thinking about, like, how do we make this better? And how do we bridge the gap between what is a traditional education? Regression, ANOVA has been around since I don't even know when, but that's sort of what has been the first year graduate sequence in every social science discipline. How do we go from that type of material into the advanced material more gently, more gradually, if you will? And in doing so, how do we make sure that students remain conversant in traditional measures? So the words that people use to describe things is what I'm actually referring to. So, for instance, when I first started talking about this in a faculty meeting at the University of Nebraska, and we were talking about how we wanted to start changing some of the courses, a few of the faculty got very nervous and they were like, "You mean you're not going to teach ANOVA anymore?" Like, no, we're going to teach ANOVA. We're just going to do it this way so that it's a building block of something that you can add to and it's not just its own container called ANOVA. So to be effective, you have to be able to communicate with people who learned methods in a certain way, and you have to be able to communicate in a way that allows you to build your toolkit to get the newest and coolest stuff. So, our solution...
Could I say something really quick about that?
Yes, please. Go ahead.
So this is just a personal thing, kind of like I don't know. Would you agree that sometimes in stats or in any kind of graduate course that the terms that sometimes people use, that they're overcomplicated, and I don't know, sometimes I get the impression in the courses I've taken that they're complicated to shut people out as opposed to, bring people together in understanding, if that makes sense.
Yes, for those of you who can't see all of your classmates, I'm seeing several smiles and nods of agreement. Yeah. A very cynical view would be that if you can take an idea that already exists and relabel it as something you invented, then you have a contribution that's new and different, and then you have a name for yourself because you have this contribution, and it is at times relabeling or reinventing the wheel. And there are people, I'm not going to say who, I'm not going to get in trouble with potential colleagues, but there are people that I know personally and that I've seen give talks and had conversations with that seem to go out of their way to make shit harder than it needs to be. And I don't know why, but I think part of it may be because they're trying to create an air of, I know more than you. There's job security in that, for instance. But I think your intuition is not wrong. I am the opposite.
And I would even say, like, even outside of stats, like some of the terminology, like there's a 20-30 page article on this one thing that could be summed down to like maybe 2 pages. I know that's maybe a little cynical of me, but I don't know, that's why I appreciate, like, when I talk to people, I don't want to, because I feel like I even sound like I'm a know-it-all when I'm trying to talk to people who aren't in whatever, like in the same program or something. So anyway, that's just my personal reaction to this.
Well, I thank you for that reaction. I share that reaction, and what I would say is that it is helpful to learn different ways of expressing the same idea that you can pull out of your pocket to talk to people differently when you need to. So it's, I think there's a term for it. It's code switching. I don't know if that's an offensive term or not. Does anyone know that? Basically, when you speak to people differently depending on who you're talking to is the idea that I want. So like when I explain what I do for a living to my mother, that's a different conversation than when I meet a colleague at a conference and I talk about whatever I'm working on for research. So the more ways that you know how to explain something in a more complex way that they may be familiar with versus a like bring it down way that can be more helpful pedagogically, I think being able to go back and forth is useful. So registers, is that like code switching?
Yeah, like the way that the formality that you use with people is like that. We went over that in a lot of the foreign language courses, the education courses that I took, like the words that we use changes based on the audience sometimes. But yeah. I agree with what you're saying though.
Yeah, that's exactly what it is. And have a comment, elitism, potentially, yeah. I feel like some of it honestly is. And some of it may just be that this is the way they learned it and they don't know how to talk about it any other way. So, by the way, the best thing that you can do to teach yourself how to talk about something in multiple ways is to teach it. Because when someone says, yeah, I heard you, but I don't get it. and you got to pull something else out of your hat to get the message across, that is how you really start to understand things at a level that cannot be replicated otherwise. So teach it. That would be my advice to you. Anywho, so speaking of teaching, so in cahoots with my better half, Jonathan Templin, we developed this course we called it a bridge course. Literally, that's what we started calling it. I don't remember the official name, but we offered this course and we pitched it as the in-between between like the classes you had and where you want to go. And the first time we offered it, we had 54 people show up. I'm not exaggerating. We have a clarification on code switching. Okay, so maybe it's not the right term. So my apologies. Thank you for clarifying. I wasn't sure about that, but what I mean to say is just when you speak to people differently based on who you're talking to, that's what I want to say. So I don't think that should be a problematic phrase. Thank you for clarifying. So we had this bridge course, and the first time we taught it, we tried to pack in way too much stuff. Like you would not believe the mutiny that happened. We had these weekly homework assignments that took people hours and hours and hours, and like we heard about it from everybody. Like, what are you doing to my students? All they talk about is how hard you're making them work. So after substantial revision, we've backed it down into what is now this class. Basically, we've reduced it to sort of the bare bones of what I think are the building blocks you need to take with you so that the next classes are not quite so overwhelming. And it's based on this idea of Legos. So there's 4 building blocks. First one, linear models. So that's what you have in your pocket so far. Estimation is the second one, which means different ways of getting the answers, the numeric version of the responses for to answer your question. Link functions, which is how you predict different kinds of outcomes that aren't necessarily going to be continuously distributed. And if you pick up these 3 things in this course, then that will make you better equipped for Lego number 4, which he and I sort of disagree as to whether this is the same thing or different things. Technically, they're the same, but they're used for very different purposes. So the 4th Lego is random effects and latent variables. So random effects are used in the context of modeling data that have dependency. So if you have a repeated measures design, if you have a longitudinal design, if you have a clustered design of multiple subjects within multiple groups, like students in classes or teachers in schools, that kind of thing, then random effects models are used in that context. And I teach 2 different courses on multi-level models, clustered and longitudinal flavored. That's also what's known as mixed effects models, by the way. Those are synonyms. So if you take, for instance, design of experiments, Ariel will talk about mixed effects models. He's talking about multi-level models at the same time. Then the other side of it, latent variables, are used in the context of statistical models for measurement purposes. So the idea that you can get a better version of a construct if you collect multiple measures about it, multiple items, multiple outcome variables, etc., and then you can use what they have in common as its own new thing. What they have in common is the latent variable. You basically take the covariance amongst multiple measures measuring the same thing, you put it in a circle and you give it a name. And that forms the basis of structural equation models. So once you understand these 3 building blocks, the rest of that stuff in number 4 comes much easier, because then not everything is new. The problem that we had before is that we went from linear models and tried to teach 2, 3, and 4 all at the same time. And that did not go well. So I'm hoping that this goes better. So linear models, what do I mean by that? That's the idea of putting predictors in a model to answer research questions, deciding what kinds of effects they should have. So for instance, of a quantitative predictor, is it a linear effect only, or is it a nonlinear effect potentially? Do the effects need to have interaction terms to add moderation? Is an effect significant after controlling for X, Y, and Z covariates? The questions about unique effects. Most research questions are phrased as linear models questions. So that is the core of everything that we do in quantitative methods is linear models. It's really important to have a solid handle on that before adding on further blocks. So we are going to talk about linear models as well as to follow up on your previous coursework. They are taught in ways that are more or less intuitive for adding to them. So the more intuitive way to approach linear models is from a regression standpoint, the general linear model framework. And that's the way that Brandon, I believe, was teaching 6243, the way that I'm teaching it, the way that I taught 6242, if you had that with me. Less intuitive is sort of an ANOVA approach that's focused on sums of squares for particular kinds of designs. That type of strategy sometimes obfuscates the linear model that underlies the ANOVA. And so that's one thing that we'll practice next week is like when you say you're going to do, say, a two-way ANOVA, what does the model look like for that? Because if you need to do an ANOVA, say, to predict a binary outcome or to predict a count outcome or to predict anything that's not normal, you got to know the linear model representation for it. So those are flavors of the GLM. So in terms of language, the GLM is unique in that it's the only set of models that I know of where there are different names used as a function of what kind of predictor variables you have. Everything else is named with a different set of criteria than that, but predictor variables in particular. So what do I mean by that? Well, if I predict an outcome that's supposed to have normal residuals, so we'll just say it's a continuous outcome, and I have one quantitative predictor, you might find a chapter on that in an intro stat textbook called Simple Linear Regression. If you have two quantitative predictors of a quantitative outcome, people would call that multiple and sometimes throw in the word linear. Linear means different things to different people. We'll talk about that in just a bit. If I switch out my predictor and I have it be something that's categorical, so a grouping variable, for instance, and I only have two groups, that would be in a chapter called an independent samples t-test. If I have a grouping variable that has three or more groups, that's another chapter called one-way analysis of variance. If I have two categorical predictors, then somehow automatically included with it would be an interaction term between them. Then we have two-way analysis of variance. If I pick up a quantitative predictor in addition to my categorical predictors, then we're in the world of ANCOVA, with the C meaning adding covariates. So this is all one model though. That's what makes this crazy. All these different words are talking about just permutations that have to do with what kind of predictors got included in the linear model. Can I distinguish linear models from effect size? So effect sizes are much more general. You would have an effect size as a way of judging the size of an effect in a scale that is readily interpretable. So for instance, in a correlation metric of R that goes from -1 to 1, or D, standardized mean difference metric that goes from basically absolute value 0 to infinity, you can convert any linear model slope into one of those effect sizes. Does that help?
Yeah, it really helps.
Okay,
Thanks.
good. Yes, please keep the questions coming. I'm watching the chat window, looking in between the camera and the chat window here as I'm pinging back and forth. And if you have all of these things happening at the same time, then people just give up and call that multiple regression in some cases. But these are all one thing. And why they are all one thing is because of what we assume about E. E is the ticket here. So I will tell you that the notation that I favor is a mishmash of population notation and sample notation that you'll see in the textbooks, because this is the way that I see it in academic articles and books a lot of the time. You're taught in your first intro stat classes that you're supposed to use Greek letters for population notation, and you're supposed to use Roman letters, regular letters for sample, and then that falls apart real quick. So I have this sort of hybrid thing where in the notation that I use for this class at least, the betas are the fixed effects. So these are the estimated constants. So for instance, beta 0 would be our intercept. Beta 1 is the slope that goes with x1. Beta 2 is the slope that goes with x2, and so forth. Also important in notation, the i's. The I subscripts are to indicate any variable that varies across individuals, whereas terms that do not have an I are estimated constants. So the model has the same beta 0 for everybody, the same beta 1 for everybody. That's what I mean by fixed. We don't know what it is. We estimate it from the data, but it's one value. It's fixed. So we can throw in x1 and x2 as grouping variables, quantitative variables, nonlinear terms like a quadratic term. We can do it whatever we want. E is what makes it a general linear model. So E is a residual. It's the idea that the model isn't perfect. We are going to have some discrepancy between what the model says your outcome should be and what it actually is. What the model says your outcome should be has the little y hat thing, the little caret thingy on the top. So that's why I have the second line here. This is the linear model portion. What we assume about E is what makes it a general linear model. So the general idea is written more formally like this. We are saying that Y is squiggle. Anyone want a vocabulary quiz here? What does squiggle mean? Tilde.
Does it mean it's distributed on?
Ding. Yes. I also use tilde to mean ish when I write things. Like it's about 2, squiggle 2. Yes, normally distributed with a mean of y hat and a variance of sigma squared e. So we're using population notation here, even though this is coming from a sample. That's what I mean by mishmash. And I think it's okay because we know that the population is really just a concept. We never actually know what it is unless we make up the data. So y hat is what we know. The e variance, residual variance here represents what we don't know. So y hat, a term that you're going to hear repeatedly throughout the semester here, is conditional mean. It's what the model says y should be based on the predictors. Some friends really let them down and let them mishmash. I'm not sure I get that.
It was the joke that Farhan made. Friends don't let friends
Smush? Yeah.
Someone's friends let them down and let them mishmash.
Yeah. Notation is always author specific. That's the thing. Everybody has their own way of writing things. You know, I put things in bold in my slides for emphasis, and someone else would probably yell at me and say, no, bold is for matrices. So I have a convention. There will rarely be matrices in my slides. Let me put it that way. I will make a point of telling you if it's a matrix because my mind just does not think that way. So conditional mean y hat, residual variance. So in addition, to use these models, you have to be willing to assume a couple of things. The big one, and the thing that is still true for everything we're going to do in the first half of this semester, is that the residuals are independent. Meaning that the e's are not more correlated amongst subsets of people than others. So when would that not be true? Any guesses? This is the audience participation portion. Yes, go ahead.
I do have an answer, but would that be considered cheating because I've taken the longitudinal course?
No, that would be me setting you up to provide an answer.
Yeah. Okay, yeah, so
yeah.
longitudinal data tracking over time or people from different groups.
Yep. So if you measure the same person repeatedly, the e's from their observations are going to be related. And if you think about multi-level data in terms of groups of people, teachers who teach at the same school may have e's that are related. Students who have the same teacher may have e's that are related. That's what I'm talking about. So general models and generalized models, those words are for independent samples. So you can control for any dependency via fixed effects. For instance, let's say, Andrea, I'm looking at you, even though you're just hanging out with us. If you have, say, different TAs leading sections of the same course, and the TAs are responsible for grading, do you think there might be variation in scores based on who graded your paper?
Yes.
Yes. Empirically, yes. So in that case, you could either fit a multi-level model if you had lots of TAs, that's building block number 4 that you'd need to pull in, or you could basically treat TA ID number as a categorical predictor and control for it that way. So then after you control for who graded your paper, the residuals are then independent. That's the big one.
Is there ever a truly independent, like, isn't there always some sort of trend that is going on, even if it's minute?
It's an empirical question. This is one of those things that I don't know of a way to test it if you don't already have an idea as to why it might be violated. It's not something that you can see in like plots of residuals or things like that very easily. You kind of have to think about how the data were collected and then plausibly how could the responses be bunched together. That would be my best advice, which is admittedly generic, but that's what I got. The other two things that general linear models force us to assume is normality and constant variance. So if you sign up to estimate a general linear model, this is what you're agreeing to. And the reason why you are forced into those assumptions is tied to the use of the normal distribution. The normal distribution is characterized by a mean and a variance. A variance, single. The same residual variance is supposed to apply to all the cases. That idea is illustrated well in a picture that I stole. So I've started making sure I put the attributions of where I find things on the internet. This is who I stole it from. Thank you very much to this person for making this picture for me so I didn't have to. But the idea is that along the regression line here, the model is assuming that the e's are normally distributed at each point, so they're equally spread out. A way to think about that is that the model is doing as good a job for people who are low on X as for people who are high on X. One residual variance that holds for everybody. When would that not happen? Something like this. So the not good picture, and yes, I stole this from someone else. I thought this was terribly effective. This picture is heterogeneity of variance instead, or heteroskedasticity, one of the longest words that I know. Non-constant variance. So there's a good example of a switching. If I want to sound like I know what I'm talking about, it's heteroskedasticity. If I'm teaching, it's not constant variance, right? Not the same. But this type of picture right here, where the e's spread out, this is really common in outcomes where the outcome can't go below some point. For instance, like count data. If you're trying to predict the number of things that have happened and somebody has 0 or 1 thing or 2 things, there's not as many ways to be wrong as if you're trying to predict that they have 50 things and they could be off much more because there's much more variation possible at the high end. So one of the nice features of the models that we'll cover is that a lot of them have built-in fixes for normality and non-constant variance together because they're working with a different distribution as its assumption. So these three things that you're assuming, independence, that's one thing. Normality and constant variance are a consequence of the normal distribution. So what do we do if this is broken? We find a different model. So that's linear models. The idea of is there an effect? And you know general linear models, which forces us into this bin of assuming certain things about the residuals that may or may not be true. What else you need besides linear models to adequately analyze any outcome is dictated by two things. How the outcome is measured, that's building block number 3, link functions. We're going to do that all semester long. And how many dimensions of sampling that you have. So is it just occasions within persons, or are people also nested in groups such that it's occasions within persons within groups? So there's two different kinds of dependency happening. And that dictates what kind of random effects or latent variables you need. How we are able to add on these additional building blocks beyond linear models is by changing estimation. So finding a different way of getting the answers is required once you step away from the general linear model. So least squares is what you're taught first. That whole idea of calculating sums of squares for the model and then sums of squares for the residual and then you got your total sums of squares and all that stuff, we can't do that anymore, even if I wanted to, which I don't, which is why I don't spend a lot of time on it, because I know what's coming and I know that that's not going to work for very much. So least squares is fine up to a point, but it quickly becomes impractical for most real-life data analysis problems. Maximum likelihood is where we're heading next. That picks up where least squares leaves off and offers us a lot more flexibility. And then Bayesian analysis picks up where maximum likelihood gives up. Bayesian is used for two distinct purposes. One is philosophical. I'm not going to go into that. The other is computational. There are certain kinds of problems where finding the best set of answers to a lot of things at the same time is just numerically not tractable, particularly if you don't have a lot of people. And so Bayesian analysis can be a workaround for maximum likelihood for those certain types of problems. That won't be necessary in our class, but it is necessary once you start combining link functions and latent effects. So in the world of item response theory models, for instance, the world of structural equation models, the world of multi-level models predicting not normal outcomes, then you start to get into situations where you may have to use Bayesian estimation instead of maximum likelihood just to get results at all. But we're focusing our efforts this semester on maximum likelihood. So is that a term you guys have heard before? Maximum likelihood? Farhan, question?
Yeah, can you explain link functions again?
I haven't explained it yet.
Yeah, but like the stuff you did mention, you said something like it says about the outcome.
Yep. The way that you are able to trick your general linear model into predicting something that's not normal is through link functions.
Okay.
That's all I've said so far.
All right.
It's coming, I swear, though. This is me establishing intrigue, right? It's like, you got to stay tuned. That's what most of this class is about, is link functions. But in order to be able to use them, we have to change how we do estimation. That's where I'm headed. So ordinary least squares can find the answers in some kinds of data. And what the answers are determined to be are the ones that optimally minimize the sum of squared errors. That's how you choose which ones you keep. There are different ways of deciding what the best answer is. You know, I could look at a data set and be like, I think the slope is 4. That's an estimator. 4 may not be the slope value that minimizes the sum of squared errors. That we just decide that that's what we're going to go with in terms of how to get the best answer. Do fixed effects mean main effects? Sometimes. Fixed effects more generally are intercepts and slopes. The fixed part means that they are constants that are estimated from the sample data. Everybody gets the same. As opposed to random effects, which means everybody gets their own, which we won't be talking about until April. Okay. So we can do sums of squares. And this is how people used to do things before they had computers to do other things. So there's a lot of algorithmic computational stuff that can be done by hand if you work within this minimizing the sum of squared errors as the way to estimate things. The good news, though, is that we're not stuck with that. Maximum likelihood offers a lot more flexibility in the kind of model you can build. So for instance, if you're trying to predict an outcome whose residuals aren't normally distributed, if you're trying to predict more than one outcome at a time, if you're trying to predict outcomes that have dependency or clustering, or incomplete data, that's another big one. So everything that you've learned about minimizing the sum of squared errors is literally the same thing as maximizing the residual likelihood. So there is a flavor of maximum likely called like REML. I'm checking the transcript. Did it get it? REML? Are we still at REMO? REML. Can I get a confirmation? No. No one wants to play? REMO? Okay, we're still at REMO. Ramble. Oh, that's a new one. That's Zoom being like, okay, Elise, move it along. They got it. No more ramble. We need that emoji, right? The move it along emoji. That would be useful. Anywho, REML, as it is pronounced, is residual maximum likelihood. So maximizing the likelihood of the residuals is mathematically equivalent to minimizing the sum of the squared errors. So you can get to the same place, it's just a different, I would say a different approach, because REML is more general. So OLS calculations that you learned in terms of all the sums of squares stuff are just computational shortcuts to doing maximum likelihood. And the best place that I've found that explains this to you is on your reading list. Craig Ender's book is about missing data analysis, but he has the clearest explanation of how maximum likelihood works that I've ever seen. So I assign his chapters 3, 4, and 5, I think, in all my classes that use maximum likelihood. So if you're interested in how the math shakes out to be the same, go listen to him or read what he has to say. For now, though, I can tell you this. If you understand the basics of this, a tape measure, then you can do maximum likelihood. Because all we're doing is finding a height. And the tallest height wins. That's how maximum likelihood works. Height of what? Height given by a distribution. So here's our friend, the normal distribution. I stole this picture from Wikipedia. And this is the machinery that underlies our model if you're talking about general linear models. You have a mean, you got a variance. So this is an example from just a distribution that doesn't have any predictors, but the same is true once you start adding predictors. The mean is the conditional mean given by the model, not just a mean for everybody that they share. And for any observation in the sample, this formula right here spits out a number on the y-axis. It's height. How likely is that person's outcome given the model parameters? So if the mean is this and the residual variance is this, how tall is this person's data? And if we stick with an empty model, we can check our math in Excel or we can check our math in software. So this is the thing that I posted to the webpage today. I have a spreadsheet and a SAS program to demonstrate this concept. So here is this. I'm going to eject from the slides for a second and switch over to my spreadsheet so you can see this in action. Okay, I can zoom in the spreadsheet, but I can't zoom in the formula. All right, I don't know if you can see that. It's a function that says norm dist. Excel has that normal distribution function formula programmed into it. So for instance, let's say that I have this set of data and I want to know what the mean and the variance are for this set of observations. Well, we have formulas for that, but what if we didn't? So I can start out with, let's say, a guess. Let's go over to the red here. I think the mean of these observations is 5.24. I think the variance is 2. Let's try that out and see how it goes. So if I think the mean is 5.24 of these observations, and I think the variance is 2, there's my height for that person. Norm dist. Down below, there's my height for the next person. There's my height for the next person, and so on. So likelihoods, if you want to combine across people, are supposed to be multiplied if people are independent. But multiplication of very tiny numbers like that is a nightmare. So to make it numerically more stable, what people do in practice is take the natural log of that number. So the formula function rather is ln in Excel. So minus 5.75 is the natural log of that height. And if I'm working with logs instead, to be able to combine across people, all I got to do is add them. So here is my sum of all of the numbers in this row. So that minus 27, it's a weird number, but it's a number. That represents the height combined across all of my data. That's plotted by this red line. Well, I know that this isn't the right answer because I have a handy dandy formula for the mean and the variance, and the correct answers are over here. The mean is actually 5.19 and the variance is this. So if I plug in the height, I find the height with those two values instead, I get the green answers. The log of that is this, and that's the blue line here. So maximum likelihood is used to find the answers in an iterative fashion. It tries a set of values, calculates the height, tries another set of values, calculates the height, until it gets to the combination of model parameters, just mean and variance here, that make the data the tallest. Tallest wins. So that's how it knows when it's done. When it's come across the values that are optimal for the sample, it's the ones that make everybody combined the tallest. So if we look at the difference between the red line and the blue line is the correct answer. The red line is taller for some people. So people who have higher values, having a smaller variance makes their data taller, but it's at the expense of other people having shorter, less height, shortness. So it's tallest for everybody at the same time. And so this number, the sum of the log likelihoods, that number will show up on your output as an index of model goodness, where taller is better. So if you estimate these models in stata or M+, that's the number that would show up. And indeed, I have estimated this in a SAS program to show you that this is the number that shows up. Also more commonly, elsewhere in the SAS output, you will find this number. It's -2 times the log likelihood. And that is because if you multiply the log likelihood times -2, then you can directly compare log likelihoods across alternative models. And the difference between -2 log likelihoods is distributed as a chi-square. AIC and BIC are other fit statistics that show up that are combinations of likelihood with corrections for the number of parameters. Question: is maximum likelihood related to the R-square of a linear regression model? No. It's a different thing. So there's two different questions to be answered. Let me see if I can explain this. First question is what I'm talking about here. Like, given the model, what is the best possible set of answers we can come up with? What should the mean be? What should the variance be to make the data the tallest? That's what we're trying to figure out. Whether that model is any good is R-square is a separate question. So yeah, 1 second for a follow-up. So if we were to add predictors, for instance, in maximum likelihood, that should make the data taller. Adding predictors should also make the R-square increase. So I think you could say the difference between models in log likelihood is related to R-square, but not the log likelihood itself. These values don't have meaning in an absolute sense. They only have relative meaning to other values tried as the possible answers, and then other models tried as the best description of the data. It's all relative. Okay. Other question, I repeat the statement about -2 log likelihood? Yes, this is something we'll talk more about in the second half of the semester. Actually, it'll be sooner than that. This number right here, the sum of the individual natural log of the heights, that's log likelihood. Taller is better. So higher numbers are better. So if I have a model that makes my data taller than another model, that new model is better. Taller wins. In practice, though, to make it easier to compare between models, you have to multiply the difference in log likelihood by 2, -2 to make the direction go the right way. And so output for certain programs tries to save you that step. And it takes the log likelihood and multiplies it by -2. And that's what it spits out for you instead. And if you're looking at -2 times the log likelihood, now you've flipped it backwards. Shorter is better, smaller is better. That term is often called deviance in the multi-level modeling literature, and I think that's a good way to remember it. Like deviant behavior is bad, you want less of it. -2 log likelihood is deviance. So in regular log likelihood, sum of the individual observations, higher is a better fitting model. Once you multiply it by -2 and switch the direction, smaller is the better fitting model.
So if you were, I think something just clicked. So like when we're comparing models, like if we did like AIC, for instance, then this is like predictive weight between model. Like the higher the predictive weight, the higher the height of the likelihood. Is that correct?
So AIC and BIC are one of many different information criteria statistics that are used to adjust the height for how many parameters it took to make it that tall. So if you can make your AIC and BIC smaller, because for whatever reason they are always times -2 log likelihood, not likelihood. So across programs, AIC and BIC are smaller is better, even if the program gives you likelihood instead of -2 log likelihood. So these things are additional pieces of information that basically correct how tall your data are for as many parameters as it took to make it that tall. So like it's taller, but I had to add 50 predictors. Like is it taller enough to justify having 50 predictors? AIC doesn't think so. Okay. Other questions? Is larger the absolute value of -2 log likelihood the better? No, it's the number. So like this tiny number here, higher would be a less negative number. Closer to 0 would be taller. So there's no absolute value. It's just because these are tiny numbers that you take the log of, and that's why we end up in this negative space. Sure. So what if I told you
Lisa,
that, yeah, go ahead.
sorry. Do we have two parms? Parms is parameters.
Do you have what? I'm sorry?
Parm in row 21. Parm.
Oh, parameters.
So do we have two because we are using mean and variance, no?
Ding. Yes. This is an empty model with no predictors because I can't do anything more complicated than that in Excel.
Thank you.
This is pedagogy, folks. Do not do this on your own. Like, this is just to make a point. But yeah, that's where the 2 came from. Thank you for foreshadowing. Because where I was heading next is why these? Why mean and variance? Because we're using the formula for normal. Well, what if I want to predict something that's not normal? Like, I don't know, an outcome that's binary. So I only have zeros or ones. Well, if I have binary data, those residuals can't be normal. They also can't have constant variance, which we'll talk about. Okay, cool. How about if I swap out the height then and instead use the Bernoulli distribution? So that one's not programmed in, but I have it. It's basically the probability of a 1 if you got a 1 times the probability of a 0 if you got a 0. It's the easiest one. Okay, now I have a different underlying distribution that I'm using to calculate height because it's a better match for the data. Same story. I have my height, I take the log, I take the sum. There's my log likelihood. And now I only have one parameter because the mean determines the variance in Bernoulli data. So if you have a variable that has a mean of 0.5, meaning half your observations are 0 and half of them are 1, then you have variance of 0.25 because it's the proportion of 1s times the proportion of 0s. That's what gives you your variance in binary data, and as you move away from that even split, the variance shrinks. So there's no separate parameter for the variance because we don't need one. Not in binary data. Here's binomial data. Number of correct responses out of so many. So like test scores are binomial, for instance. You can convert that into percent correct or things like that. Guess what? I got a formula for that one too. Excel has a binomial distribution. Okay, cool. Plug in that formula. I get a height for each person. Take the log of it, sum it up. Now I'm in business. So you just look at your variable and you figure out, okay, which kind of distribution should I use to calculate height? And you swap it out for a new one if you need to. That's how this works. The last one, even I looked at it this morning and I was like, what is this? Yeah, I was trying to figure out the beta distribution. Oh my God, that's a horrible one. And I can't explain this to you. I tried to figure this out many years ago and I have no idea what these numbers mean at this point. But I know that the parameters of the beta distribution are expressed differently in different places, and I was trying to figure out how SAS did it versus Excel did it versus whatever. We're not going to do that one. That one's too hard for me. So, anywho, this is the spreadsheet that you guys can play with if you'd like to. You folks can play with, because literally all this is height. So we're just changing the way that we measure height for different outcomes. So you don't have to assume something is normal if there is a better height measure than normal for that type of data. Okay, height. Yep. Where are we at? 134. Time flies when you're having fun, isn't it? Says no one but me. When I first started teaching in this time block of 12:30 to 1:45, I would continually keep going. And eventually, like at 1:55, someone would be like, yeah, class ended 10 minutes ago. Oh. All right. I was here. Where we go? Questions while I find where we were and try to wrap things up for today.
Can I do a quick summary of what we talked about with the estimation thingy?
Yep.
So we figure out the distribution of the outcome, and then we find the parameters that would maximize the probability of getting the data if those like parameters were the parameters.
That is conceptually correct. For discrete distributions, it's probability. So like
likelihood, yeah.
And if it's a continuous distribution, it's likelihood.
Mm-hmm.
But conceptually, they're the same idea. They both are heights.
Yeah. So we would call it the likelihood of the data.
Yeah. Yes.
Okay.
The likelihood of the data given the parameters. Mm-hmm.
So we do that for different values of the parameters, and the way we find out which one maximizes the height is we do that whole computation with the log likelihood and -2 and everything, right?
Yep.
And the software will like do this for us. We don't have to compare.
Correct. So that's the SAS program. I fed these same numbers into SAS, and I did proc mixed, which is a maximum likelihood estimator, and it spit out these log likelihoods, and that's how I made sure my formulas are working.
All right.
Mm-hmm. So there are certain cases where people have mathematically figured out a shortcut to what has to be the tallest height. And so like the formula that you know for mean and variance, that's where it came from. It's a shortcut. The formula for the mean for a binary distribution is a shortcut. They're all shortcuts for very simple cases, but once you start getting into predictors, some of those shortcuts no longer apply. And so then it's a brute force. Okay, what's the height if I try this number? Okay, what's the height if I try that number? And the one that makes it the tallest wins, where there's a convergence criteria that each program sets where how much taller does it have to be before it's willing to give up and call it good? And if it keeps trying values and it's not getting any taller, then it's like, okay, we're done, and sends you the output. and it uses calculus to figure out where it's at. and that's my version of estimation. So it's trying to find the slope as it gets to the top. And if it's the slope is this way, it knows it needs to try a higher number. And if it's over the top and it's going down and the slope is negative, it knows it needs to back up. And how back up by how much depends on the acceleration of the slope, like how tall, like how steep it is. And it's all calculus. And somebody else figured this shit out so I don't have to. Ta-da! Told you I'm not a statistician. If you want the details on how to estimate things and how the calculus plays in, head on over to the stat department, the biostat department, or talk to the person who's currently parenting upstairs. He will be happy to hook you up. He has forgotten more about estimation than I will ever learn in my lifetime. Anywho, all right, 138, link functions. That's where we're headed here, because we can't just change out the formula for height. We got to solve another problem first. And that problem is that linear models keep going. So let me just foreshadow what's coming next. I'm going to skip a few slides for a moment and get to this one. So let's say that I have a binary outcome. I'm on slide 31, just to give you a taste of what link functions are, since I introduced the word and didn't really explain it very well. And then we'll talk about it next time. So if I'm trying to predict a binary outcome, I'm using a Bernoulli distribution. It has one parameter, which is the mean. The mean is the proportion of observations that have a 1. So functionally, what I'm trying to predict for each person is their probability of having a 1. If I know nothing else about a person, I guess the mean. Well, half the sample has a 1, so your probability is 0.5? Okay. Then you put in a predictor. Try and refine that prediction. Okay, based on your characteristics, now I'm going to give you a more refined guess as to your probability of a 1. So let's put in my X predictor. This is a linear model, right? Linear. And what happens? If I'm trying to predict the probability of a 1, uh-oh. For very high values of X, I'm going to predict that you are absolutely a 1, 120% a 1. And for very low values, you are absolutely not a 1. Negative 20% a 1. So this is the other problem we got to solve, because we have to have a model that understands what is logically possible based on how the outcome was measured. We need it to do that. We need the model to understand that it has to shut off at the boundaries of what is possible. For binary data, that's a 1 or a 0. So that S-shaped function, otherwise known as a logistic function, is our link function. You are going to have this memorized by the end of the semester, I guarantee it, but I will tell you that a logit that creates this S-shaped function is the log of the odds of the probability of a 1. That is a link function. What it does is create an outcome that goes on forever and ever from negative to positive infinity. But when you back translate this thing, this y, a logit, into probability, it stays where it needs to. So a logit is a let me back up. A link function is a transformation of the conditional mean that allows us to use the same old linear models that we're used to and not go out of bounds. How many of you are in IRT this semester? Quite a few. Guess what this is? This is a 2-parameter IRT model. That's what this is. The only difference in IRT, X is a latent variable. In this class, X is a variable that exists in your data set. It's the same thing. And that's why I think this class, foreshadowing, will be helpful if you're learning IRT as well as structural equation models, that try to predict binary outcomes, ordinal outcomes, and so forth. So normal distributed outcomes are continuous. So we don't have to worry about going out of bounds. For anything that we have to worry about going out of bounds, we need a link function to make sure that we stay within bounds. That's what they're for. And there's a whole bunch of them. Logit is probably most common. Log is another very common one, and there's several more that we'll talk about that are less common. But that's what they're for. Cool, huh? So I took IRT without knowing what a logit was for the entire semester. 4 years later, I audited a class as a postdoc where they talked about logistic regression. That's what this is right here. And I went, oh, shit, that's what this is. I get it now. So I want to save you from 4 years of confusion as to how these things are related.
I have a really quick question before we go. So
Yes.
for the one on the left,
Yep.
so that would be like if you tried to graph, like let's say that each one of those points were like, sample data, and then you put it into like a general linear model, it would produce that.
Exactly.
Okay.
Yep. So the general linear model for binary data is broken for 2 reasons. The line keeps going as 1. That's fixed with the link function. And then ease can't be normal with constant variance is the second. That's fixed by swapping out a new distribution to calculate height width. So it's 2 different problems, 2 different solutions, link functions and distributions. So this semester is going to be all about mix and match. What kind of link function do we need? What kind of distribution do we need?
Is there like a flow chart almost of like how to
Yes.
decide?
Very
Okay.
much so.
Okay.
Yep. But it's 1:44, so I got to wrap things up for now. As much as I would keep going, but there'll be another class that needs my attention. So any other last second questions?
Yes, Lisa, I have a quick question.
Yes.
What is the difference between logic and logistic function?
A logit makes the logistic function.
Really?
Yeah. So if you predict the logit with a straight line,
Yeah.
and then you back translate that logit outcome into the probability, then you get this S-shaped function.
Nice.
Yep.
Thank you.
Yep. This is our next unit, by the way. We're going to do this in much greater detail. This is just a demonstration of the idea. So, all right. Then I will say goodbye for now. Please try homework 0. Let me know if you have any problems. I have office hours at 3:30. If anybody wants to ask more questions, or emails are always welcome too. I hope to see you next week in person. We'll see. So, until then, stay warm. Thank you for coming, and I will see you.
Have a
Peace
good
out.
day. Bye.